Hello, in this video we're going to be finding area between curves expressed as functions of x. So let's just do a quick review of an integral. So if I want to find the area of the region in the first quadrant bounded by y equals the square root of x, the x-axis, and the line y equals 4, that means that I want to find the area of this shaded region right here. And back when we started learning area, we talked about Riemann sums, where we said I can draw a rectangle. The base of this rectangle is some delta x, and the height of this rectangle is going to be the square root of x. Now I have a whole bunch of rectangles, so I'm going to call this x sub I and delta sub I of x. So the area of this rectangle is going to be my delta sub I of x times the square root of x sub I. And if I add up all of these rectangles, so I'm going to add up the area of all these rectangles, I should say. This is what I get. And I'm going to say from I equals 1 to n, depending on however many rectangles there are. And then we said if I shrink the length of this delta I sub x, in other words, if I take the limit as n goes to infinity, so I want to increase my number of rectangles over and over and over again. So let's say now I have infinitely many rectangles. I'm going to get the area of this whole shaded region. So that was our basic understanding using Riemann sums. We translated this into finding an integral. So here I'm integrating in terms of x. I'm integrating from 0 to 4. And I'm integrating the square root of x dx. Keep in mind that this is the same thing as x to the 1/2. So when I integrate, I get x to the 3/2. Oops. I have a 2/3 out front, and I want this from 0 to 4. So I'm going to plug in, I get 4 to the 3/2 minus 0 to the 3/2. Keep in mind that 4 to the 3/2 is 4 cubed square rooted. The square root of 4 is 2. 2 cubed is 8. So I really get 2/3 times 8 minus 0, but really just 2/3 times 8, and that is 16 over 3. So that is our first example. So this is a little bit of a review, but I want to extend it to what if this was our area? So I'm used to integrating one function from a to b, and that gives me my area under the curve. But what if now I want the area between two curves? So if I do the same thing where I draw that initial rectangle, the base of that rectangle is still some delta x, some change in x, what would the height of that rectangle be? Well, the height would be my original function, let's say h equals, and I'm going to say f of x minus my g of x. That would be the height of this rectangle. So if I want to find the area of the whole shaded region, just like we did in the review question, I'm going to integrate now from a to b, but I'm going to integrate f of x minus g of x, and that's with respect to x. And so for each of these problems, we're going to ask ourselves, what is the height of each rectangle if I were to draw in my rectangles? And the way that it works is the height of the rectangle is always going to be the top function minus the bottom function. So that's what my students end up memorizing. And if convincing you that the height is f of x minus g of x, let's say f of this value, let's say that's 4, and let's say this one is below the x-axis, so let's say that's -2. What would this height be? Well, that's going to be this 4 plus this 2, which is going to be 6. So 4 minus negative 2 gives you that 6. So if we want to put numbers in there, we can. But it's always going to work out where it's the top function minus the bottom function. So this is the idea of what we want to do today. Let's do a few examples. Let's try to get it all on the screen. So let's start with number 1. This says find the area of the region bounded by y equals x squared and y equals negative x squared plus 4x. So sometimes they will give you a picture of the graph so that you can see what you're doing, and sometimes they won't. When they don't, you want to start by finding points of intersection. So we're going to do that first. To find points of intersection, I'm going to set the two equations equal to each other. So I'm going to say x squared equals negative x squared plus 4x. I'm going to get everything on one side and a 0 on the other side, and then I'm going to factor. I have a GCF of 2x. So this tells me x equals 0, x equals 2. Now y equals x squared, I know is this basic, whoops, could have drawn that better, this basic parabola. And y equals negative x squared plus 4x ends up looking, let's put my 2 right here, ends up looking like this. So the region that I want to find the area of, I want to find the area between the curves. So that's going to be this area. All right, so let's set up step 1 was to find our points of intersection. Step 2 is to actually find our area. So I'm going to find my area between x equals 0 and x equals 2. So those are the bounds of my integral. And then if I draw a rectangle, my base is delta x. Your height, we want the top function minus the bottom function. Well, this top function is the y equals negative x squared plus 4x minus your bottom function, this function, is your y equals x squared. So you can simplify this work in your integral if you want, or you can do it over on the side. It doesn't matter. But keep in mind this is going to be negative 2x squared plus 4x. So that is what I am integrating. Okay, so let's do our integral. I'm going to get x cubed, negative 2/3 out front, plus I'm going to have x squared. 4 divided by 2 is 2, and I'm evaluating this from 0 to 2. So let's start with negative 2/3 times 2 cubed plus 2 times 2 squared minus, and when I plug in 0, notice I just get zeros. Simplify from here. 2 cubed is 8. 8 times 2 is 16, so I get negative 16 over 3. And then here, 2 squared is 4. 2 times 4 is 8, so I have negative 16 over 3 plus 8. Get common denominators. I get 24 over 3. Simplify, and we get 8 over 3. And that is the area bounded by these two curves. So that is our first example. We have a couple more for you. Number 2, find the area of the region bounded by f of x equals e to the x and g of x equals x, and by the vertical lines x equals 0 and x equals 1. So here we have a picture of the graph for you. Here's x equals 0, here's x equals 1. We want to find the blue area, which is the area between the curves. So I'm going to go straight to my area. I want the area from x equals 0 to x equals 1, so those are the bounds of my integral. And if I draw my rectangle, my height is going to be my top function minus my bottom function. Your top function is your e to the x, and your bottom function is y equals x. So I am taking my integral of e to the x minus x, top minus bottom, dx. When I do that, that's going to be e to the x minus 1/2 x squared. And we're evaluating that from 0 to 1. When we plug in, I get e to the 1 minus 1/2 minus, plug in 0, e to the 0 equals 1, and I'll get minus 0. This is going to be e minus 1/2 minus 1, which is e minus 3/2. And that is our second example. The third example gets a little bit more complicated, so let's talk about it. Number 3 says find the area of the region bounded by y equals sine of x, y equals cosine of x equals 0, and x equals pi over 2. So I've gone ahead and I've graphed this for us, and I want you to notice if I'm thinking what is my top function, what is my bottom function, from 0 to pi over 4, your top function is y equals cosine of x, and your bottom function is sine of x. But that changes after x equals pi over 4. Your top and your bottom functions switch. So when they switch, that means that you need two separate integrals. So my first integral is going to be from, what are your x values, 0 to pi over 4. I'm stopping at pi over 4 because that is where my top and bottom functions switch. So from 0 to pi over 4, we said your top was cosine, minus, we said your bottom was sine of x. And then I'm going to say plus, now I want to integrate from pi over 4 to pi over 2. From pi over 4 to pi over 2, your top function is sine of x, minus your bottom function is cosine of x dx. We want to integrate both of these, so the integral of cosine is sine. The integral of sine is cosine, but it's negative, so you're going to have negative cosine of x. So I'm going to say plus cosine of x. We're evaluating those from 0 to pi over 4. Plus, integral of sine is negative cosine of x. Integral of cosine is sine, so I'm going to have negative sine of x. And we're evaluating from pi over 4 to pi over 2. So I'm going to have sine of pi over 4 plus cosine of pi over 4 minus sine of 0 plus cosine of 0 plus, running out of room, let's move down here. Plus negative cosine of pi over 2 minus sine of pi over 2 minus negative cosine of pi over 4 minus sine of pi over 4. Okay, let's fill in these values. Sine of 0 is 0, cosine of 0 is 1. Negative cosine of pi over 2, cosine of pi over 2 is 0, so this is going to be 0. Sine of pi over 2 is 1, so this is going to be minus 1. Minus cosine, let's see, cosine of pi over 4 is rad 2 over 2, so this is going to be negative rad 2 over 2 minus rad 2 over 2. Keep simplifying. Rad 2 over 2 plus rad 2 over 2 is just going to be rad 2. And then I'm going to get from here minus 1, and this is going to be negative rad 2 with this negative out front, so this is plus rad 2. So we end up with 2 rad 2 minus 2 as our answer. And that is how we tackle when the top and the bottom functions switch. We always split it up into multiple integrals. Now, I want to note for this problem, you could understand that we know that this first area is equal to this second area. So we could have just set up one of our integrals and multiplied it by 2 and not worried about the second one. but I wanted to show it to you this way because this way works anytime your top and bottom function switch. And that was a few examples of finding area between curves expressed as functions of x. Thank you for watching.